Welcome to the 2018 IEEE APS Student Design Contest. This is a video demonstration of our working system, as well as an overview of its development process. We are RFbusters, a team from the Department of Electrical and Computer Engineering at the University of Patras, Greece. But first, let us introduce ourselves. My name is Christos Hassis, and I'm a fourth-year undergraduate student specializing in the field of telecommunications.
My name is Georgios Evangelou. I am a third-year undergraduate student, also an active member of the local IEEE student branch, and I'm interested in electronics and signal processing.
My name is Maria Foukaeos, and I am a fourth-year undergraduate student specializing in the field of microelectronics.
Hi, I am Styliani Kaliba, and I am a second-year undergraduate student, mostly interested in the field of power and energy. And now that we go to present our team, let us proceed with the system overview.
Let's begin with a top-down dissection of our proposed solution. Starting with the antenna elements, the W5030 radome omnidipoles comprise our selection of the receiving elements. Approximately 17 cm in length, they provide an optimal solution. Type N female to SMA male adapters are necessary for the signal transfer through the coaxial cables. Moving on, the single-pole double-throw RF relays, powered by a 12 to 24 DC volt boost converter and controlled by a single GPIO pin, will be responsible for selection of each individual antenna pair. Hosting the operating system and the signal processing software, our single-board computer will be responsible for the required data processing and display. Finally, bridging the gap between these two, the ETUS B210 is the software-defined radio platform of choice due to its outstanding characteristics and value.
Now, let's get right into the signal generation methods we used to test the real-life performance of our implementation. After inserting a USB memory stick and configuring the desired modulation is shown, we can go ahead and export the waveform into a binary format file according to our predefined parameters. We will use the preset seed hex value of 1FF for now, and we'll switch over to the spectrum analyzer. After saving the aforementioned parameters, we apply the preset modulation, and thus we have an exact representation of the transmitter to be located.
At the time of recording this video, the replacement for our malfunctioned SDR device has yet to arrive. Thus, the following graphs stem from equivalent simulations of the algorithms we designed. This is the GNU Radio Companion. We opted this software platform as it provides great flexibility and compatibility with our chosen software-defined radio device. In its high-level programming environment, each block represents a unique and customizable function or data structure. Consequently, one can create complex functionalities and programs in a flow graph-like representation. This is our angle of arrival estimation flow graph. Because of the target signal being direct sequence spread spectrum and not easily distinguished while noise and various interferes are present, we use a correlation-based method to find the time difference of arrival in two receiving inputs. In this simulation, varying the delay in one of two inputs, we see the peak and thus the time difference of arrival sliding in time. We apply the cross-correlation function between the two inputs, and the resulting graph possesses our peaks at the time difference of arrival. This can then be easily converted into an estimation for the angle of arrival. This method has the advantage of not requiring the pseudo-noise sequence that the signal was modulated with. The center frequency and bandwidth of the signal are sufficient. To measure the delay spread profile, we firstly import the generated file containing the PN sequence that modulates the signal. Using the same program we created for the angle of arrival estimation and replacing one input with the simulation of the modulated signal, the generated graph now possesses peaks at each individual multipath of the signal. Inspecting these peaks, we can derive the characteristics of each multipath and thus map the delay spread profile.